This podcast is brought to you by LMU Munich.
Okay, thanks. So I had slides, but this thing is not working. So I'm going to do chalkboard talk, old school. Hopefully it doesn't slow me down too much, but I don't think it's going to be a problem. So just to get started, one thing I wanted to say in the introduction was that Lee Smolin, who was one of the 4 people who started the field of loop quantum gravity, calls Julian Barbour the grandfather of loop quantum gravity, because at the time that Lee was coming up with his ideas about using holonomies to represent the field variables to quantize in quantum gravity, he was visiting Julian in College Farm and hearing a lot about Julian stressing the importance of background independence. So what I like to say is that there's now a new approach to quantum gravity called shape dynamics, which I want to tell you about today. And if Julian was the grandfather of loop quantum gravity, then he would be certainly the father of shape dynamics, because it was definitely his ideas about Mach's principles and about the nature of scale, the fact that we shouldn't be able to detect it, that helped develop this field. So today I wanted to tell you, this is going to be a kind of personal account of how Julian started this idea of shape dynamics and what it's turned into today. So it's going to be informal. I want to have a little bit of fun with it. So I'm going to tell you the story. I'm going to try to tell it as a story. A story of shape dynamics. And I also am going to apologize for my spelling, because the little red lines don't come underneath it when you do it on the blackboard. And I'm talking to potentially historians in the audience, and I'm really embarrassed about my English. Okay, so what is shape dynamics? Okay, we mentioned it a couple times. So shape dynamics is locally scale invariant theory of gravity. And it's mostly equivalent to general relativity. But there are some differences, and those differences are potentially important and potentially very interesting. Okay, it has, in comparison to GR, it has a new notion of time, and we like to think that it's a new improved notion, potentially improved notion of time. It has a new and potentially improved notion of symmetry, which is very much based on the kind of things that Harvey was talking about, the conceptual ideas from Mach's principle, and in particular, the influence of Poincare Ì. But it also excludes certain types of singularities. So the singularities in general relativity that come from focusing theorems are avoided in shape dynamics. And also, it's a new starting point. It provides a new theory space to explore for quantum gravity. So I'm going to try to tell you a bit about what it is, and in particular, how it was developed, because I think that's interesting. So, like I said, I wanted to tell this like a story, as like a kind of play. So in any story, there are the main characters. Okay. Yeah. So you can't even read my handwriting, probably. So I might not even need to write it on the board. But for us, of course, one of the main characters is the space-time metric. So I'll just write G mu nu. So this is the thing that tells you locally what distances are in general relativity. But this thing has an alter ego in terms of spatial geometry evolving in time. So you can break this thing up into the spatial metric, G, so just distances in space, and the lapse, which happens to be the 0, 0 component of this thing, and the shift. These guys are less important. But also, the key thing is that there's also a G dot, so the time derivative of the metric, which is related to its momentum. Okay, so those are those are the main characters. But another thing that's important is the Einstein-Hilbert action. So the thing that tells us how, well, in this picture, in the space-time picture, it tells us what space-time should be, which space-times are selected by the dynamics. But on the alter ego side, it tells us how the spatial geometry should evolve in time. So this guy, which I won't write down, in the alter ego side, it turns into a Hamiltonian. So the Hamiltonian formulation of the Hamiltonian for general relativity has the same form as the Hamiltonian that you would have in standard particle mechanics. So it looks like a p squared plus v minus the energy equals 0. But except for p and v are different, and e are also different. So in general relativity, you have the momentum, then you have some metric on the space of momenta, and that's the kinetic term. The potential is just the spatial curvature, and then the energy, there's a minus sign, the energy is 2 times the cosmological constant. So the cosmological constant is interpreted as the thing that's kind of pumping energy into space. So energy in space means that the spatial metric is fluctuating more rapidly. So this guy here is going to be our antagonist. He's the bad guy. He's the villain of our story. Because this is the guy in the quantum theory that is giving us all kinds of problems. And it's also the guy who's contributing to interpretational issues, to the timelessness of the theory. So let's see. Okay, I'm not going to mention that. There's also the protagonist, the hero. And this is the guy who's going to generate, so what do I mean by generate? This is the guy who, in the Hamiltonian theory, is responsible for scale invariant. So when you apply him as an operator, imagine in the quantum theory, if you applied him as an operator to your states, you would get local conformal transformation. So it looks like, it doesn't really matter what it looks like, but it's the metric times the momentum. And this thing is the generator of local scale transformations. And he's the hero of our story, because this is the symmetry that we want to try to implement in gravity. Okay, so, okay, I got to erase, I think. The next, so any story starts with a prologue. And so our prologue is going to be the kind of prehistory. And by prehistory, I'm going to mean everything, because it's a personal story, everything that happened before I met Julian, all right? So it started with, so the first really important person in this is Dirac. And in 1959, he figured out a way of actually fixing a particular clock synchronization. So of course, we know that general relativity, you can pick any clock synchronization procedure that you want, and they're all supposed to give you, be able to describe equivalent physics. That's the kind of physical way of stating foliation invariance. So the invariance of general relativity under arbitrary choices of space-like foliations. Let me draw a picture. This is space-time, t and x. And you can take slices of this space-time, or you can take a different slice. And these different slices represent different clock synchronizations. So Dirac figured out that you can choose a particular clock synchronization by requiring this constraint, so that this constraint here chooses for you a particular surface of simultaneity. So that was Dirac's observation in 59. Then in 71, York had a very important paper where he realized that you can use we'll call this Dirac guy the CMC, because it's constant mean curvature. It's not that important. I'll just call it this. So York realized that you can use this choice of clock synchronization as a way of solving the initial value problem of general relativity. So if you want to, so this is related to Harvey's comments about Poincare Ì. If you want to be able to know how to evolve general relativity, there's an indetermination problem in the initial value formulation. And you have to find out a particular choice of initial data that actually satisfy the constraints of the theory, satisfy the symmetries of the theory. And York figured out a procedure for doing this. And since that time, it's the only known procedure that is known to work for the most general case. So this is the thing that numerical relativists still use today exclusively to do that. Now in his paper, well actually not the original paper, but a couple papers later, he said, I'm just going to read the quote, "An increasing amount of evidence shows that the true dynamical degrees of freedom of the gravitational field can be identified directly with the conformally invariant geometry of three-dimensional space-like hypersurfaces embedded into space-time." So he had this picture already 40 years ago that gravity was about evolving conformal geometry. And it was in 2002 that Barbour and Anderson, who was our other speaker, and a couple other authors, Neil Lamorihue, Brendan Foster, and I think Brian Keller, in 2002, who found a variational principle for general relativity that implements this idea of, well, it implements the identification of the degrees of freedom of the gravitational field of York. So York had this ontology that gravity was about local shapes, and Julian and Edward and other people realized that you can derive general relativity using a variational principle that implements this idea. So this is setting the stage, okay? And then, so now, that's the prologue. The next thing I really wanted to talk about is the setting. So every story has a setting, which is the location that all the events happen. And for me, I was very fortunate in 2008 to be able to visit Julian in his house in Oxfordshire. So I have a picture of it. So I'll just show you the picture. Or maybe I'll turn the laptop around. I don't think you guys are gonna be able to see. It's a little small. So imagine a beautiful farmhouse in Oxfordshire, where Julian invites physicists, young physicists, old experienced physicists, to talk about physics. And I happened to sort of go there. And basically, just to give you, so the reason why I wanted to bring this up is because it's a sort of, Julian is one of these people that has a foot in two rooms. What's the expression? Foot in two counts. Anyway, foot in two places. One of them is this sort of historic setting. I think this house is built before the Principia. And on a typical day, what we would do is, Julian would make bread and yogurt. Then we would go, and he has his famous back room where we have like very intense discussions about the nature of reality, or the nature of gravity. And then in the afternoon, we would sort of just walk through the countryside and look at birds, and then also discuss physics. And then finally, in the evening, Julian would go to bed and we would do calculations by the fire, which I also have a picture of, but you can't see it. So anyway, it's a very different environment from the sort of mainstream physics environment. And I think that one of the things that I benefited from is just the sort of peace and tranquility to sort of focus your mind on one particular problem. Now, the contrast to this is the Perimeter Institute, and that's the other foot that Julian, the other count that Julian has his foot into, which I'm not going to even do. It's this really crazy-looking building that looks like it's a rocket ship about to take off. I don't think I can show it either, but for those of you who are in the front row. And a very important thing happened. In 2009, he gave a talk at the Perimeter Institute on telling us this idea that he had in 2002. And that's where Tim Kozlowski, the author of that, and Enrique Gomez were in the audience. Oh, Enrique Gomez wasn't in the audience, but Tim Kozlowski was. And that's where Tim said, if this is true, maybe we could do something really interesting with this quantum gravity. So that was the beginning. That talk was really the beginning of like the modern version of shape dynamics. So, okay, that's all the setup. Well, no, I wanted to say that it's the sort of the technical sort of hyperactivity at Perimeter Institute mixed with the kind of historic setting, I think was the led to, well, I don't know what I'm trying to say. Okay, so the plot. So what's the plot? So now we're getting to the meat. I've done a lot of setting up. So shape dynamics is based on two key ideas. It's not based, it's motivated by. The first one is that all measurements, I'm not going to write it, it's going to take me too long. All measurements of length are local comparisons. So if I want to, at the end of the day, you can reduce all measurements of length to saying, I have an object, I want to measure its length. I put another object beside it, and I compare the two. So if that's true, then why is the absolute scale of these two things important? It's not directly observable. It's the kind of thing that Mach wouldn't like. Because if I take the size of both of these objects and I double it, or triple it, or quadruple it, it's going to double both the size of the object I'm trying to measure and the measuring stick. So that in the end, the result of the measurement is changed. And furthermore, if I quadruple space over there and double it over here, if I walk over here, I do my measurement again and the measurement is local, it still doesn't change the result of the experiment. So this motivates a particular symmetry, which is, and really, I think one of the key insights was that it's about the spatial metric. This is an observation about measurements of length, not about proper time. Should be that we should require that our theory of gravity be invariant under this symmetry, where we take, we multiply the metric by a conformal factor, which is x-dependent. So we can blow up space independently at every point. So we're looking to try to implement this symmetry, which is the guy that was generated by our protagonist here. The second key thing is that scale invariance is kind of sufficient condition for quantum field theory to be well defined. So the technical statement of that is that if it's scale invariance is a symmetry exhibited by quantum field theory at a fixed point of the RG flow. So this is the kind of thing that we're looking for in a theory of gravity. We're looking for a fixed point. We know that there isn't a Gaussian non-fixed point. That's a statement of the non-normalizability of general relativity. But maybe there's a different way of thinking about the theory where we can find something having to do with the spatial. Because everyone prior to this was still thinking about the space-time. How much time do I have?
Just over 10 minutes.
Okay. Good. So those are two kind of one is quantum mechanical, one is sort of a philosophical motivation. But both of them point to, this is an interesting symmetry to study and to see if you can implement it in general relativity. But now we come to the conflict, which is that if we take this symmetry and we plug it in to the Einstein-Hilbert action, well, this is the 4 metric. It's not invariant, and you can see that it's not invariant very easily because this is a spatial symmetry and this is a space-time theory. Now, more specifically, what happens is that the Hamiltonian for this theory, if I call this symmetry T, so I just call this conformal symmetry T. If I perform a conformal transformation to the Hamiltonian, it's not phi independent. So this is the problem. This is really the key problem: is that if I do a conformal transformation to the Hamiltonian changes. it depends, yeah. So, but the interesting thing, which is sort of the observation due to York, is that it fails to be zero at every point in space, and always. So not only is this thing not scale invariant, it's sort of maximally not scale invariant. Somehow these two symmetries are completely in conflict with each other. And in some sense, you can think of this many-fingered time evolution of general relativity as being orthogonal, completely orthogonal to this symmetry. And that's actually the key property that we can use to our advantage. So now I'm going to draw, so the resolution to our conflict is that despite the fact that scale invariant, this symmetry is not a symmetry of, not a kind of symmetry of this action, we can still use this to construct a theory of gravity which is scale invariant. And I'll show you, I'll just draw a picture to motivate how this is done. So now this is a surface which lives in the phase space of general relativity. So this is the space of all possible momenta, all possible metrics. And this is the surface that is the Hamiltonian equal to 0. So this is the surface that general relativity lives on. Okay? Now, what I said here, that this thing is kind of not equal to 0 everywhere, is equivalent to saying that there's a surface, and this is our protagonist, pi GAB equals 0, that cuts this surface exactly once. So our protagonist is basically slashing our antagonist, cutting him through the middle, exactly once. Pardon? Yes, I know. That is true. So it depends on your perspective who's the good guy and who's the bad guy. That is definitely true. But actually, this picture is quite nice because it allows us to understand the York method. In the York method, you have an arbitrary point on this space, and you want to be able to project it down to here. But nobody knows how to do this projection directly. So what you do instead is you project onto this surface. That we know how to do. And then you can follow the gauge orbits. So these directions here are like the local conformal transformations that you make. So you go here, and then you apply a local conformal transformation, and then you hit this intersection. And this intersection is this gauge that Dirac found, this CMC gauge. It's general relativity with a particular clock synchronization. So, so we think of this gauge as our, well, okay. Now, okay, so that already explains the two things that I mentioned, the first two things. Now, the theory that Julian and Edward found, and others, was a theory that lives on this intersection. Okay, anyway, this is Barbour, Anderson, al. Their theory lives on the intersection. Now, what shape dynamics is basically what we do is we want to define a Hamiltonian evolution on this surface instead of on this one. And there's an easy way to do that. You just, here you have some kind of flow. So the Hamilton's equations tell you that you have to move in this direction on phase space. And you can lift that flow up onto any point in the surface, and that tells you, it gives you a Hamiltonian evolution on this new theory space. Okay? And this is the shape dynamics Hamiltonian, and we basically just define it by following the gauge orbits onto here, onto this theory. So using that construction, we can kind of borrow the Hamiltonian from general relativity and define a new theory which is locally scale invariant. That's how it works. Okay. So now I'm on the epilogue, which is good because I think my time is almost done. So that was our theory that we came up with in 2010. And 3 years has passed since then. So what have we been able to do with this new theory? A couple things. One of the things that is, some of you may know, be able to appreciate this better than others, but in general relativity, it's extremely difficult to figure out what the reduced degrees of freedom, what the observables are of the theory. But here, because our symmetry principle is very simple, it's this conformal diffeomorphisms, we can explicitly identify our observable degrees of freedom. And that is a huge difference because when you want to quantize the theory, it's those degrees of freedom that you want to quantize, and not the extraneous degrees of freedom that occur in the metric in the full description of the theory. So we have a clean identification of the observables, but there's a couple things. So this symmetry allows us to connect with the ADS-CFT correspondence, which is a duality in string theory between conformal field theories that live in one less spatial dimension than the gravity theory. So there's a conjecture in string theory that there are certain limits of string theory which are dual to these conformal field theories. And this symmetry allows us to really probe that and potentially explain actually why the duality works. Also, we can get rid of certain kinds of space-like singularities. So any singularity that you get from focusing theorem, so like the Big Bang singularity, initial singularity, where you have all of these congruents of geodesics coming through and the scale factor is blowing up. Those don't occur in shape dynamics because the scale factor for us is pure gauge. So they're just not there. So it's almost like in the space-time picture, you can't geodesically continue curves, but on this phase space, you can. They have a natural extension. So that gets rid of certain kinds of space-like singularities. And Julian's going to talk tonight about very new results where you can use shape space as a way of understanding the error of time. And I'm just going to give that as a preview. I'm not going to explain it anymore, but looking forward to Julian's talk tonight on that. And the last thing, and I think potentially the most interesting thing, is it gives us a new theory space, and a new theory space for quantum gravity. And since Wilson, we know that it's the theory space that really defines your quantum field theory. And because we have a different theory space, we could potentially have be able to do more. So it's a new starting point for quantum gravity. We're still working on that. We don't have it yet. Otherwise, I would have told you about that. Okay, thank you.